Dear students, in this video I am going to discuss numerical problems appeared in the year March 2020. Okay, let's get started. Let's have a look on the very first problem. See, in this problem there are two charges. They are QA and QB. QA equals to 5 microcoulomb, QB equals to minus 5 microcoulomb, which are placed at a distance of 0.2 meter. And we need to find out the electric field at the midpoint O. Let me take this one as E. We need to find out electric field at the midpoint O, as well as we need to find out force experienced by the negative charge, that is force experienced by negative charge, that is let me take negative as Q0, test charge minus 2 nanocoulomb. We need to calculate the force as well as net electric field at the point O. So here there are two charges which are placed at the points A and B. So here at A we placed plus 5 microcoulomb, and at B we placed minus 5 microcoulomb. Distance between these 2 points is 0.2 meter. And our aim is to find out electric field at the midpoint O. Let me consider this a midpoint O, and this midpoint is at the same distance because it is a midpoint, so it is at the same distance from A as well as B. So let me take this one 0.2 because of the reason that is the midpoint. So we could write this one as 0.1 meter, as well as the distance from B to O is also 0.1 meter. We know that the electric field due to the charge placed at A is acting in the outward direction because it is a positive charge. So you know that from the positive charge the electric field will be acting outward direction. So this, let me consider the electric field E1. This is E1 is due to the charge placed at A, which is acting in the outward direction, that is AO. And let me consider E2 is the electric field which is acting along OB only, because this is negative charge. Due to the negative charge, electric field always acting inward. For that reason, we can take the E2 is acting along OB. And you can see that these two electric fields are acting in the same direction at the point O. If they are acting at the same direction, then we could add them. So net electric field at O is equals to E1 plus E2. Why we are adding them? Because they are acting in the same direction at the point O. And we know that E1 is equals to E2 because the magnitude of the charges placed at A and B are same, and they are at the same distance. The point of consideration O is at the same distance from A as well as B. So distance same, as well as the magnitude of the charge also remains same. So E2 becomes E1, or E1 becomes E2. E1 equals to E2 and E2 equals to E1. So we could write that E1 plus E1 is equals to 2E1. This net electric field at O. So now we know that the electric field at O due to the charge placed at A is equals to 1 by 4 pi epsilon naught. Charge placed at A is QA divided by distance of O from A is AO square. So on substituting, that is 2 into 1 by 4 pi epsilon naught value is 9 into 10 raised to 9. QA equals to 5 into 10 raised to minus 6 divided by AO square. Here AO equals to how much? 0.1. 0.1 can be written as 10 raised to minus 1 whole square. Now we know that 2 into 9 into 5. 18 5 is 90. So 90 into 10 raised to 5. 9 into 10 raised to 6. This is equals to 10 raised to 3 divided by 10 to the power of minus 2. 10 to the power of minus 2. And simplifying this, we get the net electric field is equals to 10 to the power of 3 divided by 10 to the power of minus 2. This will become 90 into 10 raised to 5. This is equals to 9 into 10 raised to 6 Newton per coulomb. This is an electric field, net electric field at the point O. Newton per coulomb or volt per meter we can write. Now, let us find out the force experienced by the charge 2 nanocoulomb placed at the point O. We know that the force experienced by the charge is equals to the electric field at that point into charge, which is going to experience a force. Let me consider Q0. So we know that the electric field at the point O is 9 into 10 raised to 6 Newton per coulomb, and Q0, that is just charge, is equals to 2 times 10 raised to nanocoulomb, that is minus 9. This is equals to 18 into 10 raised to minus 9 minus 3 Newton, or else you can write 1.8 into 10 raised to minus 2 Newton. This is the force experienced by the test charge placed at O. So this force is acting. So because it is a negative charge, so this force will be acting along OA. Because you know that the negative charge will experience a force in the direction opposite to the direction of the electric field. Okay. The electric field is acting, net electric field is acting. This is acting along AB. Acting along AB. And this force, that is force on the charge minus 2 nanocoulomb, is acting along OA. Along OA. Okay, this is what. This is a force experienced by the charge minus 2 nanocoulomb at O. Let's go to the next question. In this problem, there are three resistances, 3 ohm, 4 ohm and 12 ohm, which are connected in parallel. Let me consider them as R1, R2 and R3. And we need to find out the effective resistance. They are connected in parallel, and we need to find out RP, effective resistance. And whenever this combination is connected to the EMF, that is 6 volt, and internal resistance 0.5 ohm, the current, we need to find out current drawn by the circuit as well as the terminal potential difference we need to find out. These are things, that is this A and in this B we need to find out. RP we need to find out as well as the current drawn by the circuit or current in the circuit, and terminal potential difference we need to find out. So here there are three resistors. Let me take R1, R2 and R3. This R1, R2, R3, they are connected in parallel. We need to find out the effective resistance. We know that whenever three resistors are connected in parallel, then the effective resistance, that is the reciprocal of the effective resistance, is equals to sum of the reciprocals of individual resistances, that is 1 by R1 plus 1 by R2 plus 1 by R3. I'm substituting the values, that is 1 by R1. R1 is here 3, R2 is 4, and R3 is 12. So I'm simplifying, we get that is 12 divided by this 4 plus 3 plus 1. So this is equals to 8 by 12. This can be written as 2 by 3. This is what 1 by RP. But we want RP. RP is equals to 3 by 2. So RP equals to 3 by 2. Or we can say that RP is equals to, that is the effective resistance of this combination is equals to 1.5 ohm. 1.5. Now we need to find out the current when this combination is connected to the source of EMF 6 volt and internal resistance 0.5 ohm. So we need to find out current in the circuit or current drawn by the battery. So we know that it is current is equals to current in the circuit is EMF and the total resistance, external resistance plus internal resistance. We know that E equals to, here E equals to 6 volt and RP equals to 1.5 plus internal resistance is 0.5. So this is equals to 6 divided by 2. So 6 divided by 2 gives us, that is 3 ampere. This is the current in the circuit. And one more parameter we need to find out, that is a terminal potential difference. We know that the terminal potential difference is equals to, that is EMF minus potential drop across the cell or battery. So this is equals to V equals to E. Here E equals to 6 minus current in the circuit is 3 ampere and internal resistance is 0.5. So this is equals to 6 minus 1.5. This can be written as 4.5 volt. The 4.5 volt is the terminal potential difference. So moving to the next question. In this problem, a NCR circuit consisting of inductor of inductance 5 Henry, capacitor of capacitance 20 microfarad and resistance 40 ohm. So we need to find out resonant frequency, quality factor as well as impedance at resonance. Let me find out first resonant frequency. So we know that resonant frequency is equals to 1 by 2 pi square root of LC. This is an expression for resonant frequency. So just you substitute and simplify, you will get resonant frequency, that is 1 divided by 2 into pi value is 3.142, square root of L is equals to 5 Henry, and C, here C equals to 20 microfarad. Micro means 10 raised to minus 6, and this is equals to 1 divided by 2 into 3.142 square root of 100 into 10 raised to minus 6. So this is nothing but 1 divided by 2 into 3.142 110 to the power of square root of 10 raised to minus 4. And this can be written as 10 to the power square root of 10 raised to, this is equals to, that is 2 into 3.142 into 10 to the power of minus 2, square root of 10 to the power minus 4. When 10 to the power of minus 2 goes up, it becomes 100 divided by 2 into 3.142. This is equals to, that is 2 1 ja 250 50 divided by 3.142. So 50 divided by 3.142 is the resonant frequency. That is 50 divided by 3.142 gives us 15.91 hertz. 15.91 hertz. So we got resonant frequency, that is resonant frequency is equals to 15.91 hertz. Or this is nearly equals to 16, that is nearly equals to 16 hertz. Okay. Now we need to find out one more factor, that is quality factor, that is Q factor. We know that quality factor is equals to omega angular resonant frequency L divided by R. So on substituting the values, that is omega R is equals to, we know that omega R equals to 2 pi for L divided by R. So substituting the values, we get 2 into pi value is 3.142 and the frequency we got now we got 16 into L. Here L is equals to 5 Henry divided by resonant resistance is 40, that is 5 1 ja 5 8 ja 8 1 ja 8 2 ja, that is quality factor is equals to, that is equals to 4, 12 point something, that is 12.568. So this is what quality factor equals to 12.568. So you can find out in another way, that is so you know that quality factor can be written as omega R L divided by, this can be written as omega R is nothing but 1 divided by square root of LC, L divided by R. So this can be written as 1 by R, and here we can write that the square root of L by C. So on substituting the values, that is 1 divided by R. R value is, here R equals to 40, square root of L is equals to 5 Henry divided by C equals to 20 into 10 raised to minus 6. And simplifying this, we get 1 divided by 40 5 1 ja, that is 5 4 ja, that is square root of 1 by 4, 10 to the power minus 6. If it goes up, it becomes 10 to the power plus 6. 10 to the power plus 6. So this is equals to, that is 1 divided by 40 square root of 100 into 10 raised to 4. We can write 10 to the power 6 can be written as 100 into 10 raised to 4 divided by 4. This can be written as 1 divided by 40, and here we have 25 into 10 raised to 4, and this can be written as 1 divided by 40 into 5 into 10 raised to 2. This is equals to 5 1 ja, 5 8 ja, 1 by 8, or 100 by 8 is equals to 12.5. This is also good, that is 12.5 we'll get. In this way also you can do. Either you can use 1 by r square root of LC, or else we can use Q equals to omega RL divided by. Okay, this is quality factor. Now let me find out Z. At resonance we know that. So let me write C. We know that Z is equals to, that is square root of R square plus XL minus XC whole square. At resonance, we know that XL equals to XC. If XL equals to XC, then Z equals to how much? Z equals to R, because square root of R square is equals to R. So we could write that Z equals to R. Here R equals to 40 ohm. So Z is equals to 40 ohm. So in this way, we can solve the problem. So at the time of finding quality factor, either you can follow this method, that is omega RL divided by R, or else we can use Q, that is Q equals to this formula, that is 1 by R in square root of L by C. Okay, either this or this, anyone you can follow. Okay, let's go to the next question. In this problem, we have equilateral prism, that is the angle of the prism equals to 60 degree, and the refractive index is 1.5. So actually, we need to find out angle of incidence. Angle of incidence, that is the angle of incidence for which the light ray just suffers TIR at the other interface. It just suffers total interreflection at the other side or other interface. So when it suffers total interreflection, just suffers, then the light ray will grazes over the surface. Okay, so let me draw the angle normally here. We know that this is R1, the angle of refraction at the interface, first interface, and this is R2, this is the angle of incidence in the second interface. Now, if we get 90 degree in the rarer medium, then this angle of incidence in the denser medium should be equals to how much? Should be equals to critical angle. We know that the conditions for TIR, the one is the light ray must travel from denser medium to rarer medium. Yes, the light ray here, the traveling from denser medium to rarer medium, and the angle of incidence in the denser medium must be greater than critical angle, but it just suffers TIR, no? So the light ray grazes over this surface. So R2 equals to C, we could write like this. So now we have a relationship between the refractive index and the critical angle, that is the sin C equals to 1 divided by n. So C equals to how much? C equals to sin inverse of 1 by n. 1 by n, n is equals to 1.5. So here 1 divided by 1.5 is how much? 0.6666. So when we use the natural sine table, we can get sine inverse 0.6666 is equals to 41.8 degree. This is the value of critical angle at this interval. That means the angle of incidence in the denser medium must be equals to 41.8 degree. But the actual question is, for what angle of incidence at the first interface the light ray just suffers TIR at the other interface? So let us find out now. So we know that R1 plus R2 is equals to, Here R1 plus R2. In the case of equilateral prism, R1 plus R2 equals to A. Just now I said R2 equals to how much? R2 equals to C. So now R1 can be written as A minus C. A equals to 60 degree and C equals to 41.8 degree. So R1 is equals to now R1 is equals to how much? 60 minus 41.8. 18.2 degree. 18.2 degree. This is R1. So you know that at the first interface, if you apply the Snell's law, according to Snell's law, we know that sin I by sin R1. When I apply the Snell's law for this first interface, we will get sin I by sin R1 is equals to here. Sin I is equals to n into sin R1. Substitute the values. N equals to 1.5 and sin R1 is equals to 18.2 degree. So now 1.5 into sin 18.2 degree is equals to how much? 0.3123. And this is equals to 1.5 into 0.3123. 0.4684. This is sin I. But actually what we want? We want I. So I is equals to sin inverse of 0.4684. So when you look at the natural sine table, we get I equals to sin inverse of 0.4684 is equals to 27 degree 59 minutes. This nearly equals to, that is I equals to 28 degree. For this angle of incidence, the light ray just suffers at the other interface. Just suffers TIR at the other interface. Okay. You can use another method to solve this problem. So by using a formula, that is the limiting value of angle of incidence. So what is that? The limiting value of angle of incidence. Angle of incidence by using this formula. So limiting value of angle of incidence, that is I is equals to sin inverse of, we know that sin A square root of n square minus 1 minus cos A. By using this relation also we can find out the I value. Just to substitute, that is sin inverse of sin 60 square root of n is 1.5 square minus 1 minus cos 60. You simplify, you'll get 28 degree. That is sin 60 value is root 3 by 2, cos 60 value is 1 by 2 and 1.5 whole square, and simplify, you'll get 28 degree. By using this formula also, we can calculate the angle of incidence for which the light ray just suffers total internal reflection at the other interface. Okay, let's go to the next problem. In this problem, we have mass of the copper coin is 63 gram, and here the mass number is 63, atomic number is 29 for the copper, and mass of the single atom of the copper is 62.92960 U, and mass of the proton is 1.00727 U, mass of the neutron is 1.00866 U, and Avogadro number 6.023 into 10 to the power 23. What is the question here? What we need to find out here? We need to find out the nuclear energy that would be required to separate all the neutrons and protons from each other. What it is called as? The energy required to separate all the protons and neutrons is called as binding energy. We have an expression for binding energy. That is binding energy is equals to, that means we need to find out binding energy. The nuclear energy that is required to separate all the protons and neutrons is called as binding energy. That binding energy is equals to delta M times 931.5 mega electron volt. We know that the delta M is nothing but mass defect. What do you mean by mass defect? It is the difference between the sum of the masses of the nucleons when they are in the free state and actual mass of the nucleus. That is the difference between the actual mass of the nucleus and the sum of the masses of the nucleons. So now let me write expression for the delta M, that is mass defect. We know that ZMP plus this is mass of the proton and mass of the neutron, A minus Z into Mn minus actual mass of the nucleus. Actual mass is the copper into 931.5 megaelectron. Now let me substitute all the values. That is Z equals to here, Z equals to 29. Mass of the proton equals to 1.00727 plus A minus Z. Here A is 63 and 29. So 10, 4 and here 5 minus 2, 34. That is 34 into mass of the neutron is 1.00866. This is the sum of the mass of the nucleons minus actual mass of the copper atom is 62. Sorry, copper nucleus is 62.92960. So into 931.5 megaelectron volt. And this is equals to, simplify this, 29 into 1.00727 is equals to 29.21083 plus 34.29344 minus 62.9260 into 931.5 megaelectron volt. So now let me simplify this one. That is 29.21083 plus 34.29344 is equals to 63.50527 minus 62.9260 into 931.5 megaelectron volt. When you simplify, we get binding energy equals to 0.57567 into 931.5 megaelectron volt. So on simplifying, we get 536.236 megaelectron volt. This is the binding energy of the atom. That means to separate protons and neutrons from a single nucleus, this much amount of energy is required. But we have a many number of atoms, that is 63 gram of copper contain how many number of atoms? Contains these many number, that is the Avogadro number 6.023 into 10 raised to 23 atoms are present. That is n number of atoms. So now the total binding energy required to break all the neutrons and protons from the 63 gram of the copper kind is equals to binding energy required to break the protons and neutrons from each atom into number of atoms present in the copper kind. This is equals to binding energy is 536.236 into number of megaelectron volt into 6.023 into 10 raised to 23. When you simplify, we get 3229.749 into 10 raised to 23 megaelectron volt. This is equals to 3229.749 into 10 raised to 23. Mega means 10 to the power of 6. Electron volt 1.6 into 10 raised to minus 19. This will become in joule. Now simplify this. We get I167.6 into 10 raised to 10 joule. This is nothing but 5.1676 into 10 raised to 13 joule. This much total energy we need. This total binding energy is this much, that is 5.1676 into 10 to the power of 13 joule amount of energy is required to break all the neutrons and protons from each other. Okay. Thank you. Thanks for watching.